This is an image of the same three light bulbs we looked at in the introduction to episode 48. I've got the same lens, the 200 millimeter focal length lens, and here you see the lens with my hand in front of it. My hand's kind of controlling the F number, limiting some of the aberration. What you see is that as I move the lens toward the focal plane, the scene gets blurry. Move the lens away from the focal plane, we find the condition where we have a well-focused image. And then we move toward the object and the scene gets blurry again. This is defocus, and we're looking at the depth of focus of this system. How we can analyze this and what it means to think about the optical transfer function in the context of defocus is the topic of today's episode. Computational imaging. Episode 50, Focus and Depth of Field. Back in episode 38, we talked about the defocus point spread function for coherent imaging systems, which is plotted here in a slide from that episode. We see that as we add defocus, the envelope, the solid line in these plots, broadens, but the real and imaginary parts, which are the dotted lines in these plots, also broaden but have high frequency oscillations corresponding to the overall bandpass of the system. If we look at the effect of that on images, this was another slide from episode 38. We see that when we have this chirped field, the high frequencies are aliased by the broadened or the oscillatory point spread function. And at the edge of sharp objects, we start to see oscillations due to the oscillatory structure of the underlying PSF. We also looked at cross sections of this chirped pattern. Here at the lower right was the amplitude of the in focus cross section, in focus chirp. As we add waves of defocus, we see very complex behavior due to the interaction of the oscillatory PSF with the object, and some aliasing and some shifting in the frequencies as observed due to this convolution between the PSF and the object. The story is quite a bit different with an incoherent imaging system. Now the point spread function is the magnitude of the coherent point spread function, or the magnitude squared. So the Airy pattern that has bipolar for the coherent system becomes this pattern for the incoherent system. And as we add defocus, we see these side lobes in the point spread function, but the point spread function is entirely non-negative, as is the object, which changes our underlying model. So if we look at the similar plots for the effect of the defocus on imaging, here we have to add a constant to the object to make sure that it's a non-negative value. And so as we get some blur, we see the mean value of the underlying signal in the blur, and the high frequencies are filtered out, and we don't see any oscillations at the edges of sharp objects. We just see a constant blur due to the defocus. Compare this again with what we saw with coherent imaging. One thing, of course, is a coherent system, if you get to a frequency that doesn't pass through the imaging system, the signal that you see is zero. Whereas for an incoherent system, every part of the object comes through the imaging system, and so if you filter out the high frequencies, you're going to see the constant valued background. And so here's back to what we saw with the incoherent imaging system. We just see the ripples that are in the object get transformed into a constant by the blur. Comparing again the cross sections, this was the cross section for the coherent system. When we go to the incoherent system, first thing to notice is that the baseline is not zero, so that the where the object has been blurred by the defocus, we get to a constant valued background. Here, this chirp should have a constant value in the original object, but the high frequencies are filtered by the incoherent optical transfer function, which means we have this characteristic triangular fall off in the transfer as a function of frequency, which is observed here in imaging and in focus chirp. As we add some defocus, of course, then more and more frequencies are lost by the fact that the modulation transfer function is reduced by the defocus, but you see some non-uniformity that some high frequency, there's a high pass filtering effect by the underlying structure of the MTF associated with the defocus that we'll look at in just a second. Another thing we looked at with the coherent system was the effect of speckle, that as we have a diffuse object, meaning that the phase at every point in the object has some random value, the in-focus object has speckle patterns associated with the averaging of that phase over features within the resolution element, and as we defocus, the structure of the speckle changes due to the changing structure of the point spread function. So we see changes in the speckle image. With an incoherent system, of course, we don't see speckle. We don't have phase associated with the non-negative valued intensity image. And as you know, a similar image that we look at with defocus, we just see the image blur. These plots are all in the GitHub site, so you can go and play with various levels of defocus yourself in the GitHub code. So that's what happens when we defocus. Let's look at how we manage defocus in incoherent systems. So, just way back review is that the in-focus image occurs when we have the geometric mean of the object distance, and the image distance is equal to 1 over the focal length. And so this is our in-focus condition. When we violate this condition, way back in episode 25, we looked at this just in a sort of ray-based configuration. So at the in-focus image, parallel rays coming through the lens come to a focal point. When we defocus, those rays blur in a bundle, and that blur is approximately linear in the defocus amount in the image distance. And so we came up with strategies based on the hyperfocal distance to manage how much defocus we could tolerate. As we've seen with coherence modeling of the field, we developed a three-dimensional transformation between the incoherent object distribution and the power spectral density distribution in the focal volume of the lens. This was that transformation that we have a transformation from a three-dimensional incoherent source distributed in these projective coordinates to the three-dimensional distribution in image space, and we had this three-dimensional impulse response, which corresponds to this focal dumbbell that we get coming into a focus and with some blur. This impulse response was the Fourier transform of the band volume function that we defined a couple of episodes ago. If we take that three-dimensional transform of the impulse response, the band volume is the modulation in these projective coordinates in Fourier space on the object distribution that we get. So we looked at the structure of the band volume, and the band volume was this interesting autocorrelation of the pupil function in these coordinates that we defined with Q being this delta x times x bar, and delta x and delta y being separations in the aperture of the lens, where the aperture plane corresponds to the Fourier plane of the space. So we can take that band volume and derive the two-dimensional transfer function because the band volume describes the three-dimensional transfer function. If we integrate out along the spatial frequency in the theta z direction, where again theta z has the form of 1 over range, if we integrate that theta z out, we have the two-dimensional optical transfer function, or in this case the defocus transfer function, describing the transfer function of the field in this defocus plane. This has the form of this integral over the band volume. We can also use the optical transfer function definition that we talked about in episode 49, where the transfer function is the autocorrelation of the pupil function, but we add this defocus term as an aberration. So you can think of the defocus as effectively part of the pupil function, and we adding that aberration allows us to derive the transfer function in the defocus plane. Now we defined so theta z is just the defocus error. Theta z is the difference between 1 over f minus 1 over zi minus 1 over Z naught. So that should be 0 if we were in the focus plane. If that's not 0, that's our aberration term. We can relate that also to the wavefront error term W20 with this equation, which is, again, back from episode 38. It turns out W20 is equal to the aperture squared times this theta z. So it's just a relation of terms people use to describe the defocus, with W20 being the most common one, dating back to work by Hopkins in the 1950s that just used standard Ziernicke expansions to describe the defocus as an aberration. So again, as we change W20, you see this impact on the impulse response. If we take the Fourier transform of the impulse response, we have the optical transfer function, and looking at the magnitude of that along the spatial frequency axis for cylindrically symmetric systems, we see that this is what the modulation transfer looks like. So this top curve is the standard optical transfer function that we talked about for a clear aperture in episode 49. And as we add defocus, you see that the modulation transfer drops. The band limit stays the same. So this aberration doesn't obviously increase the size of the aperture. So the extent over which the autocorrelation of the aperture extends is the same. So the maximum spatial frequency remains 1 over lambda f number. So this horizontal axis is in units of lambda f number. But the modulation transfer drops at various frequencies. For some levels of defocus, again, you see that there's a relative, that the modulation transfer function is not necessarily monotonic. So you can have high frequencies emphasized relative to the midband, although the maximum spatial frequency always remains at 0. We can plot the spot size as a function of defocus. Here what we're plotting is treating the point spread function as a probability distribution, looking at its standard deviation as a function of defocus. When we defined the hyperfocal distance and talked about defocus from a geometric point of view back in episode 25, we assume that the extent of the point spread function grows linearly as a function of defocus, and that's what this red curve is showing, and the blue curve is showing that this is in fact approximately true once we have a certain level of defocus away from the in-focus spot for the actual PSF. Okay, so we would like to be in focus when we form images. But objects are, we come to the fundamental problem in computational imaging. The world is three-dimensional and our measurement system is two-dimensional. So one thing we'll talk about, in a future episode is sweeping the focus and reconstructing the three-dimensional world from sequences of images where the different parts of the images may be in focus at different times. But when you look at a three-dimensional object, you can't set the focus to an arbitrary plane and have that be where everything in the field is in focus. That you have to choose some point to focus at. So way back in episode 25, we talked about this definition of the hyperfocal distance, which is in some ways the optimal distance, the optimal focus point when you want to image from infinity to some near point. You have some focal range you want to image over. So you have the choice, of course, that you could focus just at infinity, and then the object at infinity would be in optimal focus. But then everything as you come in from infinity has its focal quality degraded. So you choose instead to focus at a hyperfocal distance where you have the maximal acceptable defocus at infinity, and then as you come in, the image quality and the focus will improve, and then you get to the hyperfocal distance, the image is in focus, and you get to then you would come into half the hyperfocal distances to turn out, and you'd get back to the same defocus as you had at infinity. So your focal range goes from half the hyperfocal distance to infinity. Let's compare the derivation of the hyperfocal distance from a geometrical perspective with the derivation from the wavefront perspective that we would use in our coherence analysis. So back in episode 25, we said, okay, we want to focus so that we have a maximum tolerable blur at infinity. We set our far point to infinity, but normally that would mean that the image point, this z sub prime, the distance from the lens to the image, should be f. It's not equal to f, it's equal to the value that gives us this maximum acceptable blur, because as we come to a focus, we're going to have this blur B, and the size of B is going to be proportional to the defocus error time divided by the F number, which would be this angle here. So we substitute the Z prime in terms of ZH set at the hyperfocal distance, and solve for this ZH, and find that the ZH is equal to the F squared over B, the circle of confusion B times the F number. Okay, so this was a result from back in episode 25. Now for the wavefront analysis, we're going to say that theta Z is our wavefront error, and so if we set the wavefront error equal to 0 at the hyperfocal distance, that means that 1 over the hyperfocal distance plus 1 over Zi is equal to 1 over F at the hyperfocal distance. If we set this equal to 0, then at infinity, when this is then at infinity, 1 over F minus 1 over Zi is equal to this maximum wavefront error theta Z, and but for theta Z we'll substitute this 2 W20 over A squared, and now we solve for the hyperfocal distance in terms of this maximum wavefront error, and we find this value, and that allows us to relate this circle of confusion to the wavefront error as shown here. It's equal to W20 times twice wavefront error, but our basic hyperfocal distance is the aperture squared divided by the maximum wavefront error W20, or we could write that as F squared divided by 2 times W20 times the F number squared. Okay, so now we understand that what is the hyperfocal distance, but in a lot of cases we don't want to focus at the hyperfocal distance, right? We'd like to focus somewhere closer. So what happens to our depth of field if we focus at our preferred range? So this is our definition of the hyperfocal distance in terms of the maximum wavefront error. We could also go back to the hyperfocal distance in terms of the circle of confusion, but whatever the hyperfocal distance is, we don't want to focus at the hyperfocal distance. We want our preferred object in focus to be at some fraction of the hyperfocal distance. So we could make this Z0 whatever we want, but we can express it in terms of the hyperfocal distance by some constant alpha, the hyperfocal distance divided by alpha. And we're requiring then that if for the range of which we'll have acceptable focus, if we focus at an arbitrary value ZH, would be the range over which the defocus error theta Z is less than 1 over the hyperfocal distance. If we solve that for the allowed values of Z0, the depth of field, we get this result that if we focus we focus our lens at the distance ZH over alpha, we'll have acceptable focus from ZH divided by alpha plus 1 to ZH divided by alpha minus 1. So for example, if alpha is equal to 1, we're focused at the hyperfocal distance, and so our depth of field goes from the hyperfocal distance divided by 2 to infinity. Alpha minus 1 equals 0. On the other hand, if we decide we want to focus at alpha over 4, we would have acceptable distance from alpha over 5 to, or ZH over 5 to ZH over 3. So this gives us a way to have to find the focal stops that we need to focus from infinity to however close we want to go. That we would set the initial focus at the hyperfocal distance, and then if we set the next focus at the hyperfocal distance over 3, then we have acceptable focus from the hyperfocal distance over 4 to the hyperfocal distance over 2, covering the range that we hadn't covered, and successively setting the hyperfocal distance to ZH over any odd number. We could have a focus over a set of discrete set of focal stops from 0 to infinity. If we set alpha to an arbitrary value from this relationship, we can solve for our depth of field, which would be ZH over alpha minus 1 minus ZH over alpha minus plus 1. That difference turns out to have this value, so the depth of field goes like the hyperfocal distance divided by alpha squared minus 1, or if we're substituting for alpha in terms of the hyperfocal distance, it goes like z squared divided by zh squared minus c naught squared as a function of the hyperfocal distance. Okay, what that means, of course, is that as Z0 gets smaller, then basically the depth of field would go like Z0 divided by the hyperfocal distance. So Z0 squared divided by the hyperfocal distance. So the smaller it gets, the shorter our depth of field gets, because Z0 is always going to be less than the hyperfocal distance. Here's an example for what you might see with a SLR camera. It might have like 10 micron pixels. We have a acceptable blur. When it's going to be always bigger than 1 pixel, and let's say it gets up to 2 pixels, then we can set our acceptable blur to 20 microns. This is thinking about an F10 system. The F number determines the depth of focus. The depth of focus is how much we can allow Z sub I to vary, and basically the blur is increasing linearly as we as a function of the image space defocus. So that's not really a function of range. That independent of range, we get the same acceptable value of shifting in the image space position Z sub I. But as we translate that into object space, we're going to take a geometric mean of the image space defocus to get the change in object space, and that depends on what the relative value of Z sub I and F is. So, for example, for a range of 2 meters, we could use the equation we just derived for solving for the depth of field, the range over which the object can range, and we're going to get a range here of somewhere around half a meter, just over half a meter range at 2 meters. If we go to like a mobile device, this is again in a range of 2 meters, but the focal length is a lot smaller. And so we're dealing with a 5 millimeter focal length instead of a 50 millimeter focal length, and so the depth of field is increased because of the change in the focal length to 10 meters. If instead we focus the much closer with the shorter focal length lens, here focusing at just 20 centimeters, the depth of field is much smaller because we're much closer. So our depth of field is just a third of a centimeter. Okay, so that's how we analyze and think about the depth of field that we can accept in these systems. And these are discrete imaging systems, and so we can't have continuous sampling of the defocus everywhere. We'll always have to tolerate some defocus, and of course we can try to fix that computationally. We can do some scanning of the focus that we'll talk about later in the course, but this is the basic traditional strategy. Another thing we could do would be say, well, could we put a deliberate aberration into the lens to reduce the blur as we defocus? And so this is called extended depth of field. And so it is possible to think about in lens design. You might want to, rather than just get the best focus at the focal plane, you might want to design the pupil function with some deliberate aberration that will cause the system to blur less quickly and get extended depth of field. You can also try to design the lens to be particularly sensitive to blur. If for example, you wanted to use the lens for ranging, you might want to try to increase the sensitivity to defocus to improve your range resolution. We see here on the left is the defocus point spread function for a lens with the conventional system. So the different traces here are different levels of defocus, and the horizontal axis is in units of lambda f number. So we see on the left, as we're in focus, we have a tightly focused beam, and as we defocus, it blurs. On the right, we've added a logarithmic term to the pupil phase to try to modulate the phase in a way that it will blur less quickly. And you see we have achieved that objective, that the in-focus point spread function here is wider than the in-focus point spread function for a clear aperture, but it blurs less slowly. Now, we could get a similar effect just by increasing the f number, right? If you increase the f number, the angle that you're coming into focus is less, and so you can just stop down a lens and get extended depth of field. One advantage of doing it with an aberration instead of with increasing the f number is that if you stop down the pupil, you're going to get less light collected and so less photosensitivity. If you add a blur, you can still have a large aperture, better light collection, and maybe get some extended depth of field. As you add this blur, what you've done is decrease the MTF. So of course, for a clear aperture, your MTF is going to look like this. And here we've added this logarithmic A-sphere. We've got a kind of constant MTF as a function of defocus, which is what these different curves are, but it's constantly bad. There's a trade-off that the sort of integrated PSF over the volume, as discussed in the textbook, is constant. So by adding this blur, you get extended depth of field, but you don't get the same. You have a trade-off between the resolution you have in focus and the resolution you have in deep focus, that you can get reasonable performance over an extended depth of field, but it's much worse than the MTF that you get in the in-focus plane. There's a lot of things to unpack here. This has been a long episode. Thanks for your patience in considering this focus condition. And so we'll come back to this, of course, later in the course when we talk about computational strategies to extend depth of field. We don't have to think of this as a static system, that we can think of a system where we measure a variety of focal states before we estimate the underlying image. Of course, that's the point of computational imaging. Our image is not the data that we collect. Our image is what we can construct from the data. And that's something we're going to talk about also in the next episode, because we're going to talk about the basic idea that the measurable quantity that we have in the focal plane is the irradiance, and consider what if we considered instead the transfer function for the mutual intensity or the coherence functions. This is a plot of the ambiguity function of a pupil, which also turns out to be the transfer function for the coherence, which is the topic of episode 51.